So today we start chapter 2, which has to do with counting. And section 2.1 has to do with some of our most basic counting rules, the addition and the multiplication principle. One of the warm-up problems, a coffee shop problem, asked you to count the number of choices you can make if there's 3 different sizes of coffee that you could choose or 5 different types of donuts. And of course, if you're just choosing one item, it's clear that there's 8 choices, right? Choose one of the 3 coffees or one of the 5 donuts. So 3 plus 5 is 8. This is an example of using the addition principle. You use it all the time, we're just not really used to giving it a name. But the addition principle states that if some certain event A can occur in M many ways, and another event B can occur in, whoops, I use the same use the same variable here. It doesn't have to be the same number. Let's say n disjoint ways. Then event A or B, one or the other, can occur in m plus n many ways. Okay, this makes perfect sense. So in this case, m would represent, say, choosing a coffee, and I guess event A would be choosing a coffee, and event B would be choosing a donut. So there's 3 ways to choose a coffee, there's 5 ways to choose a donut, so there's 3 plus 5, or 8 ways to choose one or the other. Now, one thing that we want to be careful about here, when we say disjoint, what that means is pretty much exactly what it means when we talked about set theory. Disjoint sets were sets that don't have anything in common. So when we're talking about these 2 events, we need to make sure that these events don't have any overlap. Right? Disjoint means the 2 events have no overlap. And in this particular example, of course, that's the case. You're not double counting anything because there's no way for you to choose a coffee and a donut at the same time. It's one or the other. So nothing is getting double counted here. Okay, so let's look at an example of how we can use this. How many 2-letter words begin with A or B? Now, you might be tempted to actually start thinking of words here, but we're going to use words a little more loosely than you normally would. They can be nonsensical. Right, so AN is a word, and, but we also would consider AA to be a word, or AB, or AC. So it's really just a string of 2 letters. So how many 2-letter strings begin with A or B? Well, we can break this up into 2 disjoint cases as follow. First, we're going to count how many begin with A. Okay, well, like we said, AA would work, AB would work, AC would work. I don't want to list them all, but I don't really have to because I know that it's going to be anything from AA through AZ, right? And so, of course, there's going to be 26 different options here. Similarly, how many begin with AB? How many begin with B? Well, you could have BA, you could have BB, you could have BC. Don't want to list them all. But this second spot can be anything from A to Z. Whoops. And so we end up with another 26 options here. Now, these 2 options, these sets of options here, are disjoint from each other. None of these 2-letter words are going to appear on this list, and vice versa, because all of these words start with A and all of these start with B. So these are disjoint sets of 2-letter words. So how many begin with A or with B? By the addition principle, we just have to add together the number of options for event A, letters that start with A, plus the number of options for event B, letters that start with B. So by the addition principle, there's 26 plus 26, or 52 words that begin with A or B. Okay, but it's also equally important to look at a non-example of where the addition principle does not apply. So for this non-example, let's consider how many ways you can choose either a face card or a red card from a deck. We might need a review of deck of cards here if you're not familiar. When we say a face card, what we really mean there is a king, a queen, or a jack. Those are our only face cards. They're cards that literally have a human face on them. And so each one of those cards, king, queen, or jack, there's 4 of them because there's for each of our 4 suits, hearts, clubs, spades, and diamonds, we have 1 king, and we have 1 queen, and we have 1 jack. So there's a total of 12 face cards in a deck. What about the red cards? Well, the red cards are going to be any card that's a diamond or any card that's a heart. essentially is half of the deck, because the deck is half red and half black. So if the full deck of cards has 52 cards in it, then there's going to be half of those, 26 of them, that are red cards. All right, and so since this is an or statement, how many ways can you choose a face card or a red card? You might be tempted to say, well, there's 12 face cards, there's 26 red cards, so that adds up to 38 that are red or face. Unfortunately, this is wrong. This is not correct. Why? Well, an important part of the addition principle is that it has to be disjoint sets. And so is it the case that our 12 face cards are disjoint from the 26 red cards? It is not the case, right? There's some cards that are going to fall into both of these categories. For example, a Jack, King, or Queen of Diamonds is going to fall into both, and a Jack, Queen, King of Hearts is going to fall into both, right? And so in this case, we're really going to end up double counting any card that's both a face card and a red card. So addition principle doesn't work in a scenario like this. That doesn't mean that this is an unsolvable question. Of course, we've already looked at ways of solving problems like this, right? We can use the principle of inclusion exclusion, or we can draw a Venn diagram to help us. Let's say these are our face cards and these are our red cards. The overlap would be the red face cards. So that would be the King of Hearts, Queen of Hearts, Jack of Hearts, and the King of Diamonds, Queen of Diamonds, Jack of Diamonds. So there's 6 of them that are in the overlap. There's 12 total, which means there's going to be 6 face cards that are not red. That makes sense. Half of them are red, half of them are black. And there's going to be 26 minus 6, or 20 cards that are red but are not face cards. It's going to be all of the non-face cards that are diamonds or hearts. And so we sort of know from this that we can do 20 plus 6 plus 6 to find the number that are red or face. 6 plus 6 plus 20. Okay, so there's 32. Alternately, we could have just used principle of inclusion exclusion and just subtracted the number of cards that are both red and face cards. Subtracted 6 from 38 to get those 32 that we're looking for. All of this is to say, just make sure you're careful before blindly trying to apply the addition principle. Make sure that you're not accidentally overcounting things. Make sure that your 2 events are actually disjoint before you try to use addition principle. If there's any overlap, you want to use the principle of inclusion exclusion instead. Okay, so another problem in the warm-up asked, how many ways can you make a choice at that same coffee shop if you're going to choose both coffee and a donut? And it turns out we can use the addition principle to solve this problem as well, right? Remember, we said that there were 3 different sizes of coffee, small, medium, and large, and then there's 5 types of donut. I don't know what they are, let's just call them type A, B, C, D, and E. So if we wanted to use the addition principle to count the number of ways we could choose both coffee and a donut, since we're choosing both, since this is an and statement, it's not as simple as just saying 3 plus 5 anymore. But what we can do is break this up into three cases. First, look at the number of combinations that consist of a small coffee and a donut. How many ways can you choose a small coffee and a donut? Well, you could choose a small coffee and donut A, or small coffee and donut B, or small coffee and donut C, or small and D, or small and E. So there's 5 ways. Similarly, if you wanted to choose a medium coffee and a donut, there's going to be 5 different combinations here, medium A all the way down through medium E. And if you want to choose a large coffee and a donut, there's 5 options here, large with donut A all the way through large with donut E. So in each case, there's 5 different options. Now, each of these combinations are disjoint from each other because each one is choosing a different size of coffee, which means we can apply the addition principle. By the addition principle, the number of options will be 5 plus 5 plus 5. Notice we actually applied the addition principle twice here. We generalize the addition principle to more than just 2 events, in this case 3 different possible events, but it works the same way. Now, notice that because each one of these different possibilities was giving you the same number of options, 5, 5, and 5, we could rewrite this as just saying, well, 5 options times each of the 3 different types of coffee. Right? Each of the three kinds of coffee allowed for 5 different combinations because each one you were pairing with one of those donuts. And so we can see how the addition principle applied over and over again in this case really leads us to a shortcut where we could just multiply. And that's really where the multiplication principle comes from. The multiplication principle states that if some event A can occur in m many ways, and if each instant of event A allows for exactly n different ways, for event B to occur, missed a line there, then the number of ways for both event A and event B to occur is going to be n times m. This is really just the addition principle over and over again. It's saying, each instance of event A can occur in n many ways. So n for the first instance of A, n for the second instance of A, and for each of the m many ways that event A can occur, you have n possible options for event B to occur. Well, m copies of n is just equal to m times n, or n times m, if you will. All right, this is what we were doing up here with the coffee and a donut problem. Each possible way that event A could occur, that's choosing a size of a coffee, allows for 5 different ways for event B to occur, that's choosing a donut. And so by the multiplication principle, there would be 5 times 3, or 15 ways to choose both. So just like with the addition principle, we can generalize this to more than 2 events by multiplying 3 or more different possibilities. We just need to make sure that this property is held, right? Every instance of A has to allow for exactly n different ways for another event to occur. Okay, that happened up here with our coffee and donut principle, but we'll see below how that can fall apart and really not allow us to use the multiplication principle directly. So let's look at an example where this does work. Any type of problem where we're trying to count possible passwords, or possible license plates, or possible strings of letters and numbers is probably going to be a multiplication problem. So as an example, how many license plates consist of 3 letters followed by 3 numerical digits? Okay, so let's think about this first possibility here. So we have 3 letters are going to come first. Each letter is going to come from the alphabet. It's going to come from the set, A, B through Z. So there's 26 options here. And our numerical digits are going to come from the set 0, 1, 2, all the way to 9. So there's 10 possible numerical digits. All right, so if we think about filling in this license plate, essentially we're making 6 choices here. We're choosing our first letter, our second letter, our third letter, then we're choosing our first numerical digit, our second, and our third. In each choice of your first letter here, so this has to be a letter, we know that there's 26 choices here. And each choice that you make here, whether you choose A, B, C, etc., is going to allow for 26 more choices for the second letter, right? Because whether you start with A or with B or with anything here, you can still choose an A or a B or any other letter here. So by the multiplication principle, there's 26 times 26 ways to choose the first 2 letters. Similarly, this is going to allow for 26 choices in the third spot. Okay, now having chosen our first 3 letters, there's 26 times 26 times 26 ways of doing so. We now have to choose a numerical digit. I'm going to use D for digit here. Each one of these choices is going to allow for 10 different ways of choosing our next choice here, right? Because we can choose anything from 0 to 9. Similarly, we have 10 choices for the next digit and 10 for the last. So multiplying this all together, I don't particularly care what this number is. I'm just going to leave it as 26 to the 3rd power, because we have 3 factors, times 10 to the 3rd power. Multiply that out if you want, if you really want to see how big that number is, but this is really all I care about. This is how many different license plates consist of 3 letters followed by 3 digits. We want to be careful that the multiplication principle is actually going to apply, because sometimes it doesn't apply, at least not directly. So as a non-example, let's look at the case of counting the number of license plates that consist of 3 letters and 3 digits in any order. Now certainly the ones that we found up above, this 26 cubed times 10 cubed number, all of this many license plates will still apply down here. But now we want to allow for other orders. We also want to allow for, let's say, digit, 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 letter, letter, letter. Or letter, digit, 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 letter, letter, right? There's actually a lot of different ways that we could rearrange these. So the number of license plates is going to be much bigger than this. How can we try to use the multiplication principle here without, getting caught? Let's think about how this would work. If we try to use the multiplication principle, how many options do we have for this first spot here? In the last example, it was 26 because we had to start with the letter, but now we can have a letter or a digit here because we don't particularly care what order they come in as long as there's 3 of each. So there's a total of 26 plus 10, or 36 options here, right? Because it could be one of the 26 letters or one of the 10 digits. Now again, whatever you choose in that first spot, a letter or a digit, you can still choose a letter or a digit here. So you still have 36 options here. And again, on this third spot, you can choose a letter or a digit, right? Because you're allowed to have 3 of each. Now, how many options do you have for this next spot here? How many options? Can you put a letter there or a digit, or does it have to be one or the other? The question is it depends, right? Because if you had decided that in your first 3 spots, for example, you had chosen A, B, F, or something like that. Let's say you had made those choices. In this case, you would only have 10 choices left for each of the remaining spots because you've already used up your 3 letters. And so the last 3 spots would have to be digits. But if you had started off by choosing, let's say, 3 numbers, 3 digits, let's say 919. Well, now you've used up your 3 digits and you'd have to use letters here. So you'd have to use 26 options for each of these. And so each of the choices that we made in the first 3 spots do not allow for the same number of choices in the 4th spot. In one case you have 10 options, in another case you have 26 options, and in another case, let's say you had started by choosing A5G. Well, you started with 2 letters and a number, which means this 4th spot could still be a letter or a number. You would have 36 choices here, which would lead to even more questions about how many spots you would have, or how many choices you would have for the remaining spots, right? This number here, your number of choices here, is not going to be the same for any of the choices you choose in the first 3 spots. So the multiplication principle does not apply, and we're not going to be able to use the multiplication principle directly here. In the future, we'll have a way of solving a problem like that, but it requires some tools that we haven't learned just yet. So we'll see how we can use that maybe in section 2.3.